Hey everyone, and welcome to the wild and wacky world of organic chemistry. I'm Prakash, and I'm so glad you're here. Today, we're diving deep into the heart of molecules to understand the forces that shape their destinies. It's like a cosmic game of tug-of-war, with electrons as the rope, and these three effects we're about to uncover as the players. Buckle up, because we're about to explore the inductive effect, hyperconjugation, and the Mesomeric effect, three crucial phenomena that dictate how organic molecules behave, react, and interact with the world around them. Picture this. A molecule, just chilling, with its electrons humming along in their orbitals. These electrons are like tiny dancers, moving gracefully in their designated spaces, creating a beautiful, balanced dance of energy and matter. The molecule is in a state of equilibrium, with each electron knowing its place and role. But wait, what's this? An atom with a slightly stronger pull on those electrons enters the scene. It's like a new dancer stepping onto the floor with a magnetic charm, drawing the attention of the electrons. This new atom disrupts the harmony, pulling the electrons towards itself with an invisible force. That, my friends, is the essence of the inductive effect. It's a fundamental concept in chemistry that explains how the presence of different atoms can influence the distribution of electron density within a molecule. This effect is crucial for understanding how molecules interact and react with each other. It's all about the shifting of electron density through sigma bonds, those sturdy single bonds that hold atoms together. Sigma bonds are like the backbone of a molecule, providing the structural integrity needed for the molecule to maintain its shape and function. Now this shift can go two ways. Depending on the nature of the atoms involved, electron density can be pulled towards or pushed away from certain atoms, creating different effects within the molecule. If a highly electronegative atom like our buddy oxygen joins the party, it's like bringing a black hole to a picnic. Oxygen has a strong tendency to attract electrons towards itself, creating a significant shift in electron density. It sucks electron density towards itself, creating what we call a negative inductive effect, or I effect. This effect can have profound implications on the molecule's properties and reactivity. These electron-hoarding atoms are like the Scrooge McDucks of the molecule world. They gather and hold on to electron density, making the surrounding atoms electron deficient. But fear not, for there are also generous souls like alkyl groups, those chains of carbon and hydrogen. These groups are more relaxed and willing to share their electron density with the rest of the molecule. They're more likely to share the electron wealth, pushing electron density away from themselves. This creates a positive inductive effect, or plus I effect, which can stabilize certain parts of the molecule. This is the positive inductive effect, or plus I effect. Think of it as a philanthropic gesture within the molecular world, where certain groups donate electron density to stabilize the molecule. Think of them as the philanthropists of the molecule world, always willing to lend a helping electron. These generous groups can significantly influence the molecule's behavior and reactivity. Now, why should we care about this electron tug-of-war? This constant push and pull of electron density can determine how a molecule interacts with other molecules, which is essential for understanding chemical reactions. Well, this shifting of electron density has huge implications for a molecule's reactivity. It can influence the molecule's stability, its ability to form bonds, and its overall chemical behavior. It's like giving an atom a little extra oomph, or holding it back a bit. This can make a molecule more reactive or more stable, depending on the direction of the electron density shift. Understanding the inductive effect helps us predict how molecules will behave in chemical reactions, which is pretty darn cool if you ask me. It allows chemists to design and manipulate molecules for specific purposes, from creating new materials to developing life-saving drugs. Alright, let's talk about hyperconjugation, a phenomenon that's all about sharing the love, even without a formal bond. It's a fascinating concept in chemistry that shows how molecules can stabilize themselves through a kind of electron cloud sharing, even when there's no direct bond between the atoms involved. Imagine a molecule with a double bond, like our friend ethene. Ethene is a simple molecule, but it has a lot to teach us about the subtleties of chemical interactions. Those pi electrons hanging out above and below the double bond are like the cool kids in school, attracting attention from all around. They are delocalized, meaning they aren't confined to just one location, and this gives them a certain allure. Now imagine a nearby sigma bond, maybe a CH bond with its own little cloud of electrons. These sigma electrons are more localized, sticking close to their home base, but they aren't completely isolated. Hyperconjugation is like those sigma electrons getting a little starstruck and trying to get in on the action. They can't fully join the pi electron party, but they can interact in a way that spreads out the electron density. They can't form a full-blown bond, but they can overlap their electron clouds with the pi system, spreading the love around. This overlap is subtle but significant, creating a more stable electronic environment. This no-bond resonance might sound a bit wishy-washy, but it has a real impact on molecular stability. By allowing electron density to be more evenly distributed, hyperconjugation helps to lower the overall energy of the molecule. Think of it like this. The more hyperconjugation a molecule has, the more spread out its electron density becomes. This spreading out is akin to distributing weight evenly across a wobbly platform, making it more stable and less likely to tip over. And just like spreading out your weight on a wobbly platform, delocalization makes the molecule more stable. This stability is crucial in many chemical reactions and processes where the distribution of electron density can determine the outcome. This is especially important in carbocations, those positively charged carbon atoms that are always looking for some electron love. Carbocations are highly reactive and unstable, but hyperconjugation can help to stabilize them by spreading out the positive charge. The more alkyl groups attach to a carbocation, the more hyperconjugation it experiences, and the happier, more stable it becomes. Each alkyl group provides additional sigma bonds that can participate in hyperconjugation, further stabilizing the carbocation. So, hyperconjugation is like the ultimate wingman, helping molecules find stability and happiness in the chaotic world of chemistry. It's a subtle but powerful force that plays a crucial role in the behavior and stability of many molecules, making it an essential concept to understand in the study of chemistry. Get ready for some electron choreography, where the tiniest particles in the universe put on a show that's both mesmerizing and crucial to the world of chemistry. Because the Mesomeric Effect, also known as resonance, is all about electrons shaking their tail feathers and moving to the groove. Imagine electrons as dancers, each with their own unique moves, contributing to a grand performance that defines the stability and reactivity of molecules. Unlike the inductive effect, which works through sigma bonds, the Mesomeric effect operates through pi bonds and those lone pairs of electrons just itching to join the party. These pi bonds and lone pairs are like the lead dancers, guiding the rhythm and flow of the entire molecular dance floor. Now this dance of electrons isn't random. It's a carefully choreographed performance where each electron knows its role and position. The goal is to find the most stable arrangement, ensuring that the molecule remains balanced and harmonious. It's all about finding the most stable arrangement for everyone involved. Just like in a well-rehearsed dance routine, every step and movement is calculated to maintain equilibrium and minimize energy. Sometimes a group of atoms like that benevolent benzene ring decides to share its electron wealth with the rest of the molecule. This sharing creates a resonance structure where electrons are delocalized, spreading out their energy and stabilizing the molecule. This is the plus M effect, where electrons are donated to the conjugated system, creating a symphony of electron delocalization. It's like a musical ensemble where each instrument contributes to a harmonious melody, enhancing the overall stability of the molecule. But then we have the electron hoarding groups like those with carbonyl groups, who prefer to keep their electrons close. These groups are like the misers of the molecular world, holding onto their electrons tightly and not sharing with the rest of the molecule. This is the minus M effect, where electron density is drawn away from the conjugated system. It's like a vacuum cleaner, sucking up electron density and creating areas of positive charge within the molecule. It's like a game of electron keep away, but with serious consequences for the molecule's reactivity. The tug-of-war between electron-donating and electron-withdrawing groups can significantly influence how a molecule behaves in chemical reactions. The Mesomeric effect is all about understanding how these electron shifts affect the distribution of charge within a molecule. By studying these shifts, chemists can predict the behavior of molecules and design new compounds with desired properties. It helps us predict where reactions are likely to occur and how molecules will interact with each other. This knowledge is crucial in fields like drug design, where understanding electron distribution can lead to the development of more effective medications. It's like having a backstage pass to the electron dance floor, giving us a glimpse into the intricate movements that govern chemical behavior. By understanding the Mesomeric effect, we gain insight into the fundamental processes that drive chemical reactions and molecular interactions. So there you have it, the inductive effect, hyperconjugation, and the Mesomeric effect. These three powerful forces shape the world of organic molecules, influencing their stability, reactivity, and overall behavior. By understanding these effects, you're not just memorizing facts, you're gaining the power to predict and explain the fascinating world of chemistry. Keep exploring, keep asking questions, and keep that curiosity burning bright. And hey, if you ever find yourself lost in the world of molecules, just remember, electrons are just tiny dancers looking for the perfect groove. Until next time, stay curious.